Welcome to NASA Edge, an insight and outside look at all things NASA. How you doing, Michelle and Steve?
Great.
You're back for part 2 of EDL. In part 1, we talked about some cool technologies from entry systems modeling to Medley 2 and Haya 2.
Right.
And Steve, we're going to look at your second half of the portfolio. What are we going to be talking about
We're going
today?
to talk about Adept, we're going to talk about 3D Mat, and we're going to talk about heat.
Awesome. And so, just to kind of recap, for those folks that didn't see part 1, real quick, what's EDL?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to safely on the ground. So no matter what planet it is, we can do EDL.
I tell you what, when we looked at the technology in part 1, we kind of said that EDL is not easy. It's very hard, isn't it?
Yes.
And when NASA's been working on EDL for a long, long time. And so I guess as one of the things we didn't talk about in part 1 was this journey to Mars. We eventually want to send humans to Mars.
Right.
I mean, EDL is going to be one of the most important aspects of getting there, isn't it?
Yes,
Absolutely.
it is. It's one of the 2 biggest challenges that have been identified through our National Academy's reviews.
Well, what's the second one that we're going to be?
Radiation
radiation.
protection of the crew.
Oh, wow. Would you want to be on there?
Yeah, I would.
Would you?
Yeah.
Awesome.
Sign me up today.
I'll sign you up.
Now, in getting back to entry, descent, and landing, we're going to be looking at a different concept from Haya 2 from the previous show. This one's called Adept.
Right.
And I'm sorry, but I don't have it memorized, so I have to read on my paper. It's the Adaptable Deployable Entry Placement Technology.
Yes.
What is that about?
It's a way to get a spacecraft where you want it on the surface of a planet. So it's similar to HIAD in that it's a way to expand a heat shield after you get to your destination, but it's all folded up in the rocket when you launch. And this is especially useful at Mars where we need lots of drag area because we have a very thin atmosphere. But the cool thing about Adept is that it has a very high temperature capability, so we can use it at more demanding destinations like Venus or Uranus.
Blair had a chance to sit down with the TPS engineer Paul Wrzynski at NASA Ames to learn more about the Adept technology.
So Paul, tell us, what is Adept?
Adept is a new architecture for performing entry at planet surfaces. It's breaking the paradigm of the rigid aeroshells that have been used in the past exclusively for missions to other planets.
So explain how it's physically different.
The easiest way to describe it to someone is think of an umbrella. It achieves the deployed area that you need for decelerating at a planet, but overcoming the limitation of the launch vehicle that you have to fit in when you're leaving Earth. The shroud puts a restriction on how big you can make your aeroshell. So it turns out the best way to overcome that is once you leave the launch vehicle is to be able to open up to something bigger, and that's what we're doing with this umbrella.
Well, I imagine with something like that and all the extreme conditions that you face on reentry, you have to have some pretty strong material for this umbrella.
Yeah. And that's been sort of the major recent breakthrough in enabling this technology is this carbon fabric. It utilizes practically pure carbon yarns that are woven 3-dimensionally to give you a very durable surface, multiple layers that are intricately locked together. And because it is carbon is a wonderful material for high temperature applications. It is almost practically optimized for that. So carbon is a great material. You just have to be able to now get around the challenges of what to do with the material that gets extremely hot, which is what we're dealing with.
And how do you make sure that in the stress of reentry that your shield, if you will, remains deployed?
We attack that numerous ways. We do a lot of design and fabrication of prototypes to build and show that the skeleton, the underlying structure, actually functions to hold it open under the loads that we experience. That's the mechanical portion of it. The other part is the thermal portion, and that is where we look to facilities like the ArcJets to subject the carbon fabric and the underlying structure to the high temperature environments we expect to see on planet entry. It turns out though that, especially in the case of a deployable like Adept, you can do ground-based testing, but ultimately it will come down to flight testing. And the flight tests will then demonstrate sort of your end-to-end functionality, all the way surviving your launch environments, out in the vacuum of space, deploying, holding that shape and then subsequently entering, in our case for flight tests, it would be Earth's atmosphere. Now, one of the lessons that we've learned with soft goods or the fabrics is you have to be very sensitive to the scalability. So certain things may work at a meter or two scale, work great. Then you have to be careful on, do those same properties and characteristics hold as you go 5 or 10 times larger. The bottom line is you have to literally build it to actually know that it's going to work.
What are some of the big challenges you faced from a design standpoint in getting this system to work on either scale?
There are a lot of challenges. Let's make no mistake about it. We are at the cutting edge of a new technology. It has amazing promise. We've tested the fabric at a small scale in heating environments well beyond what we would expect to see at Mars. But that's at a small scale. The biggest challenges I see are just the payload that is carried along behind us is going to be exposed to environments that you maybe don't typically see for a traditional entry vehicle that has a rigid heat shield and a rigid back shell. And so that is going to be a challenge, and that's going to have to be done with analysis and test to convince ourselves that the ADEPT technology, this new entry system, can not only deliver a payload, but protect it so that that payload is still useful when it gets to its destination.
Steve, one of the trends I'm seeing in all these pieces is scalability.
Absolutely.
You have HIAD 2, you have ADEPT, which are two completely different types of EDL systems.
They are.
I remember HIAD 2 was the inflatable.
Right.
ADEPT more, as Paul was saying, it kind of deploys like an umbrella.
Right.
It's more mechanical underneath. I mean, you're testing all types of technologies, and that's what your job is at Game Changing.
Yeah, and so I think to help explain those, if you were to think about two different architectures, right? You think about maybe a Jeep car versus a sports car, right? They're both cars, but they're designed for different things.
Right.
So for HIAD, it's inflatable, right? So it's a little softer. ADEPT's more rigid body, deploys that structure. Its TPS has a higher, can handle a higher heat rate, and HIAD can handle a little bit lower, but they both have their applications.
Because there's not going to be one technology that fits every single mission.
No.
Right.
I mean, depending on where you're going.
Right. For human Mars, for instance, that architecture trade is still being conducted. And so depending on the assumptions that you make on the size of the payloads and how we're actually going to get the humans there and all the things they need to support them, the different systems have different strengths and weaknesses depending on those assumptions. So we've actually connected the EDL experts directly with the folks who are figuring out what we need to take to Mars so that they can work hand in hand on designing the best system.
Now, one of the things that I want to focus in on now in the show is, I mean, we looked at, for the past couple of systems, there were big systems, you know, with HIAD 2 and even Medley with the heat shield. I want to focus in on now on the materials, because materials are very important and what you decide in terms of, you know, can they take the amount of heat as they enter an atmosphere, right? And one of the technologies that's in your portfolio, it's called 3D MAT.
That's correct.
And that stands for Three-Dimensional Multifunctional Ablative Thermal Protection System. That's a mouthful.
It is, but it's an awesome technology.
I tell you, and Franklin had a chance to sit down with Jay Feldman, who actually is a project leader for 3D MAT. So let's learn all about that technology.
So Jay, 3D MAT. Tell us a little bit about 3D MAT and why it's a game-changing technology.
Well, 3D MAT is going to be the compression pad for Orion, the EM1 mission and all the subsequent missions. And 3D MAT is the material that we've invented, and it serves as the compression pad on the Orion crew module. If I can show you, this is the crew module. It contains the astronauts. They're inside there. And it's actually mounted to the service module through the heat shield. That's this bottom part that gets really hot when the vehicle re-enters the atmosphere.
Well, those points where it connects are where the compression pads are located, right?
That's exactly right. Those are called the compression pads. Those points are structural. They're the only part of the heat shield that are structural, so it has to serve as heat shield, withstand the heat, keep the inside cool, the astronauts cool inside, but it also has a structural job before it becomes the heat shield.
Explain to me the 3D in 3D MAT.
So this is a small piece of 3D MAT here, and what you'll notice about it is that we have fibers that run not just in the X and Y direction like a cloth, but there's actually fibers running in the Z direction. So instead of stacking layers of cloth like a 2D material, we actually have fibers running in all three directions, and we build a single woven preform, we call it, that has the dimensions that we need. This makes it very structurally robust, and if you look at this, all of the fibers are very straight. We call that a 3D orthogonal weave, and again, that lends itself to being structurally robust. For the EFT1 flight, the first flight test, that compression pad just had a 2D cloth, the X and Y direction for the fibers, and that was its shortcoming structurally. The 3D weaving is not brand new. It's been around, it is evolving, and we've pushed the technology to its limits in 3D mat, but it is used in other applications as well.
But now there's also resin in that.
Correct.
How does that all work together?
Very good question. We start with weaving, so the yarn is commercially available. It's a quartz yarn woven with our weaving partner Bally Ribbon Mills into what we call a woven preform. It's a quartz woven preform. Now we take that and we put it inside a resin infusion vessel, and we're using a process called resin transfer molding. And we essentially push resin inside all of the pore spaces between the fibers and fill, trying to get 100% of that space to be filled with the resin. And again, that makes it strong and robust.
I noticed that there's actually a giant metal bolt that goes right through the middle of the compression pad. How does that work with conducting, heat?
So the bolt is there to hold the two modules together. It's an explosive bolt so that when the crew module no longer needs the service module, the bolt actually explodes and the two modules separate, and then the Orion module can enter the Earth's atmosphere. The bolt does add some metal and it adds some thermal conductance to the system, and that is something we have to deal with. But in the first flight test, above and beyond the bolt, we had to put a lot more metal in the compression pad to handle those structural loads, and that amount of metal was really too much for these future missions, like Exploration Mission 1, where we're going a lot farther away, we're coming back faster, the heat shield's getting a lot hotter.
So Jay, what is the size of a compression pad?
Just so happens I have a 3/4 scale compression pad right here. This is the new material, 3D mat. I don't know if you can feel the weight of that.
Whoa!
Yeah, it's very, very dense, very heavy stuff.
Well, this is like it's like a dumbbell.
Yeah, it's very heavy, very dense. It's about 11 inches in diameter, and then you can see the hole, that's the representative hole where the bolt will go through.
That's a big bolt.
It is a big bolt. You only have 4 of them to hold the entire crew module to the service module, so there's a lot of load going through that.
What kind of heat stress are we going to talk about on these compression pads when this crew module returns to Earth from Mars?
So in my field, we talk about heat fluxes, and I want to give you some reference points. Everyone's familiar with the space shuttle. When the space shuttle used to re-enter the Earth's atmosphere from low Earth orbit, the amount of heat generated was on the order of, let's say, 50 watts per square centimeter. That's our heat flux. This is going to see 500, 700 watts per square centimeter. It's a significant amount of heating.
Are there any other uses for 3D mat other than using it on the crew module?
There are other potential applications. As a matter of fact, we designed it specifically for the compression pad area. It's now being used in other parts of the vehicle on the back shell where we have some both heating requirements and structural requirements, so it's already finding other uses on Orion other than its original designed one. And we have had conversations with other folks, both on commercial space side as well as the Department of Defense, who are very interested in this material. There are other potential applications.
This 3D mat material is pretty incredible. How truly is it a game changer? I know they're using it for the Orion EFT1 compression pads, but how is the material itself a game changer?
It was a game changer from the get-go. Originally thought about and designed by Ames in their CIF, Center Innovation Fund. And they saw promise back then, and they took it to an SBIR, kind of matured the technology a little bit more.
That's Small Business Innovative Research. Gotcha.
Yeah.
Okay.
And I think it was with Bally Ribbon Mills. That's who the industrial partner is. And then from there, it got picked up for game changing because it was early stage, like a TRL-3. Well, before we could even advance it, we got approached by Orion saying, hey, our simulations, our models are telling us that our compression pads are not going to hold up under the heat load. Right. But we hear that you have a material. And so they started working with us from that point forward to get it to a TRL-4.5. And now it's the baseline design.
That's incredible.
Yep.
Did I get that
really
right?
great infusion story. Yep.
Yeah.
So the idea you're taking this woven material, because you said what's a woven TPS?
It's a woven thermal protection system.
3D orthogonal design.
Yeah.
I mean, even though it's heavy, with what Jay was saying, but still, it's a great material to use for EDL reentry.
Right, so the 3D woven capability that comes from the textile industry on Earth is really applied to several of our technologies.
Right.
So the Adept fabric that covers the umbrella is just a 12-layer carbon fabric that's 3D woven. The 3D mat that we saw is quartz fiber, and what makes it really heavy is not only that it's densely woven, but then it's infused with resin.
Right.
And then we'll see, I think next, in the heat technology, they also use 3D weaving, and they do it in multiple layers with multiple types of fiber. So it's very tailorable.
Tell you what, I mean, she's proactive because she knows what we're going to be talking about next. Heat.
Yes.
HEET.
Yes.
And that stands for Heat Shield for Extreme Entry Environment Technology.
Yes.
Pretty cool.
It
And so
is.
Franklin had a chance to sit down with the TPS manufacturing lead for heat, which is Mairead Stackpole, and we're going to learn more about that cool technology. Let's check it out.
So Mairead, tell me about heat and why it's a game-changing technology.
Well, HEAT is a thermal protection material development project. It stands for Heat Shield for Extreme Entry Environment Technology. And NASA saw a need for a new thermal protection or TPS material. I think NASA has a lot of materials in the lower density range that don't do well in very extreme environments. And it also has some materials that are very heavy that do well for extreme environments. So we saw a technology gap, and the HEAT project fills that gap. It's a 3D woven system. I brought some samples along with me just to show you. So here we have an example of the HEAT weave. It's a dual layer weave. So on the outer side, the side that sees the heat, we've got a very robust 3D woven carbon. Then we transition to a better insulator. So this helps to keep the heat away from your payload or whatever is of interest you're trying to protect.
So where is this heat material? Where is it on the spacecraft?
This 3D technology covers all of the actual heat shield itself. So this would be your four-body, as we call it, thermal protection material. For the HEAT project, we have a tiled configuration that we're currently working to demonstrate. This is segmented. Each of those tiles you're looking at is a single-piece 3D woven heat tile. It's attached on and bonded on.
So why wouldn't NASA make just a one-piece heat shield? Why is it tiled?
Well, if we had a wide enough weave, we could actually accomplish that. We're currently making a 1 meter max diameter engineering test unit for the HEAT project. You can imagine as you scale up to much larger vehicles, that would be more challenging. So you'll always need a gap filler.
So when you say gap filler, what material is used to fill the gaps?
So as I mentioned, the acreage material is a 3D weave. The gap filler is also that same 3D weave. It's just softened, so it's a more compliant version. So in terms of composition, the gap filler and the tile themselves are the same.
Now, when I think of NASA missions, NASA has sent landers and spacecraft to other planets, and they didn't have any problems. What type of missions are we going to use heat on that we haven't, used it for in the past?
If you look at other missions and look at the entry conditions that those TPS materials saw, they were a lot more benign compared to the missions that HEAT is targeting. We recently just completed some ArcJet testing here at Ames, and we were at 7,000 watts per centimeter squared. The environments are a lot more aggressive. So we're targeting Venus and Saturn missions currently.
Can you talk a little bit about the resin infusion process used to manufacture the material?
This material,
Yes.
definitely. So as I mentioned, we're starting with a 3D weave. These weaves are delivered in flat planks. The woven material itself is quite formable, so I can actually take this material and change its shape. We are able to design tooling and have this weave formed in that tooling to the tile shape that we want. So it's a near net shape process.
So for instance, like the cap to the heat shield, what kind of tooling would be used to make that?
Right, so we start with a flat plank, and we have metallic tooling that we can then take our flat woven piece, form it into the nose cap shape. It is locked in the tooling as it goes through the infusion process. The infusion adds the resin, and that resin, we have a proprietary approach where we're able to add a low density resin. It's more like a foam rather than a fully dense resin phase. Once the resin is in place, it's now a rigid TPS material.
I tell you what, this heat material is really cool. If it's that good, do you possibly see using this material on all EDL systems down the road?
It could be tailored to multiple vehicles, like Orion coming back from the vicinity of the moon. In the future, we could do an upgrade. Human missions to Mars, if we use some sort of a rigid vehicle that, you know, was long and slender, it could be applied to that as well.
You know, Steve, I guess what it boils down to, we talked about this several times, EDL is tough. It's not easy. All right?
Absolutely right.
So you've got all these technologies in your portfolio that you're testing. I mean, at some point, I'm assuming in the not too far distant future, you're going to have to start looking at which technologies are the best, let's say when we first send humans to Mars.
Mm-hmm.
That's correct. And what we're finding out is that these different technologies, some of them are better applied to the different planets that we go to and their environments and attributes.
So there's not really one size fits all in this particular situation.
No, the environments are so different that we really tailor the system.
Where do you see this technology? You know, we're looking at humans to Mars in the 2030 timeframe. I mean, we're going to have to mature that and test that technology before that 2030 timeframe, aren't we?
Oh yeah, you're getting her spun up.
Well, you know, she's the one that passed Blair's initial Medley investigation, so she's experienced that.
That's
you know,
right.
I mean, bottom line is people want to know we're going to Mars one day.
Yes.
Right.
The public thinks it's cool. I mean, but we want the humans to land safely on the surface.
Right.
So the idea, and EDL is going to have to be there. If you don't have an EDL system, it's game over.
Without EDL, we're not going anywhere else and landing on another planetary body.
I tell you what, this has been an exciting for the past show to learn all about EDL from entry systems modeling, Medley 2, HIAD 2, Adept today, and then some cool material with 3D mat and heat. Seems like you've got a tough task ahead of you.
We have a lot of work to do.
Bringing the principal technology for EDL, and you have all these technologies to work on to mature them to the next level.
It's exciting.
But thank you guys for coming here today. It's been fascinating.
Thank you.
Thank
Hey,
you.
you're watching NASA Edge, an inside and outside look at all things NASA.